When you look at images like this or this, what word comes to mind? Maybe you were thinking of rust, corrosion, or oxidation. A lot of times these words get used interchangeably, but they are slightly different. They all mean that the metal is being destroyed by some sort of chemical reaction. But let's dive deeper. Let's take a look at corrosion. Corrosion is the deterioration of a metal, ceramic, or polymer as a result of a chemical reaction with its environment. So corrosion is not limited to just metals. Then what is oxidation? Oxidation is a specific type of chemical reaction that can happen to a material. Oxidation is when an element loses electrons to another element. Many metals are not in their stable form. To become stable, they need to give up some of their electrons. The process by which they do this is called oxidation. Then what is rust? Rust is actually a noun. It is the oxide that forms as a result of the oxidation process between steel and its environment. The iron in steel wants to give up some electrons, and the oxygen in the air wants to take them, and together they form rust, which is iron oxide, and this is a ceramic. Rust is specific to steel. The oxide that forms on aluminum, for example, is not called rust. Its name is alumina, but we really don't use that in everyday life. We have a common name for the oxide that forms on steel because it's so prevalent and we see it everywhere. Because all oxide films are ceramic and the oxidation process involves transfer of electrons, it may help to review the ionic bond. All that atoms want is to be stable, and being stable means either giving up their electrons or taking another atom's electrons. Look at the periodic table. Do you see the little red number in the upper right-hand corner of each element? This is the element's electronegativity. The higher that number is, the more that element wants electrons. Look at the left side of the table. The metals all have fairly low electronegativities. They want to give up their electrons to become stable. Now look at the right side of the table. These elements have fairly high electronegativities. They want to take electrons to become stable. So, if you get an atom that wants to give up electrons and an atom that wants to take electrons, then they get together and they form what's called an ionic bond. Let's take, for example, sodium and chlorine. The difference in their electronegativities is 2.1. This is large, so we would expect a heavily ionic bond. How does it work? Well, sodium wants to give up one electron to be stable, and chlorine wants to take one electron to be stable. So now we have a positive sodium ion and a negative chlorine ion. And what happens when opposite charges come together? That's right, they attract and bond. In this case, the sodium atom gets oxidized and the chlorine atom gets reduced in a reaction called redox. Redox is a reaction that combines two half reactions, reduction and oxidation. The element that is getting oxidized loses electrons, and the element that is getting reduced gains electrons. You can remember which is which by the memory phrase oil rig. Oxidation is loss. Reduction is gain. You might be thinking to yourself, but where's the oxygen? It's true that oxygen is the most common element that gets reduced when you were talking about corrosion, but it doesn't necessarily have to be oxygen. It could be an acid that is corroding the metal or another metal. So what is needed for oxidation to occur? Well, there must be electron transfer. And for there to be electron transfer, there must be an element that loses electrons. And there must be an element that gains electrons. Let's take, for example, a metal that reacts with oxygen. In the oxidation reaction, the metal will lose some electrons and become a positive ion. In the reduction reaction, the oxygen will take those electrons and become a negative ion. Then the metal ion and the oxygen ion will form an ionic bond, creating an oxide film. Now, the metal doesn't have to react with oxygen to be corroded. It could react with, for example, hydrogen from an acid or another metal. One thing to keep in mind is that this is really an electrical reaction, and therefore it happens more readily within a conductive medium. We call this conductive medium an electrolyte. In the case of rusting cars, the natural moisture in the atmosphere acts as the electrolyte. And add the salt used for melting snow on the roads, and you have a really good electrolyte. Why do some metals continue to oxidize, while it seems like other metals don't corrode at all? With the exception of a few metals, all metals will create an oxide film when they come into contact with the atmosphere. But whether you see this film or it continues to grow depends on what type of oxide film the metal creates. For example, chromium creates a clear oxide film, so we don't see it. This is the reason chromium is added to stainless steel. The chromium in stainless steel actually is corroding, but we don't see the oxide film. Another reason chromium is added to stainless steel is to protect the steel, but we'll talk about that later. Some oxide films you can see, but they just don't seem to be getting any worse. For example, silver will tarnish, copper will create a green patina, and aluminum will form an oxide layer that only makes the metal look a bit dull. But none of these metals will continue to corrode until there's nothing left of them. So how do we know which metals will keep corroding until there's nothing left and which will be protected by their oxide layer? We can determine which type of oxide film a metal will form by calculating the Pilling-Bedworth ratio. The Pilling-Bedworth ratio predicts if the oxide film that forms on the surface of the metal will continue to destroy the metal or be protective. All you need to calculate the ratio is the molar mass of both the metal and the oxide film that it creates, the density of both, and the number of metal atoms in the oxide. For example, aluminum creates Al2O3. This means that the oxide has 2 metal atoms. And magnesium creates MgO, so there is only 1 metal atom. If the ratio is less than 1, the oxide will be porous, and oxidation will continue to occur. This is because the pores allow spaces for more oxygen to reach the metal. If the ratio is between 1 and 2, the oxide film is continuous and adheres to the metal, forming a protective layer. Remember, Oxides are ceramics, and therefore they are insulators. Oxidation is an electrical reaction. Electrons can't be transferred through an insulating barrier. If the ratio is greater than 2, the oxide film will flake off and expose metal for further oxidation. So how can we prevent or at least slow down corrosion? Well, we can make the material thicker so that it takes longer for it to corrode. We can apply paints and coatings to try to shield the metal from the environment. We can anodize the metal, which thickens the naturally occurring oxide layer. This works great for metals that create a protective oxide layer. You can tell if a metal has been anodized if it is colored, but it doesn't look like it's been painted or coated with anything. We can use cathodic protection. Remember the redox reaction? The element that is getting the electrons is being reduced, and this happens at what is called the cathode. The element being oxidized and is losing the electrons is the anode. So if we want to protect the metal, we need to make it the cathode. This is the theory behind cathodic protection. There are 2 ways we can do this. 1. Through the use of a sacrificial anode. 2. By using impressed current. Let's talk about sacrificial anodes first. Have you ever heard of galvanized steel? This is where they take steel and coat it with zinc. Why would they do this? Because zinc is more reactive than steel. So the zinc will become the anode, and steel will become the cathode. Therefore, zinc is termed the sacrificial anode. We are willing to sacrifice the zinc in order to protect the steel. They do the same thing on ships. They attach several zinc bars to the hull to save the metal of the ship. In the impressed current method, this method supplies the electrons that the corroding metal would otherwise lose, thus protecting the metal.